Professor Dr. S. Gauri is the Director of EMRC of UGC and also Professor in the Department of Manufacturing Engineering, Anna University. He is the recipient of the National Award for Outstanding Academic 2011, honored by the Indian Society of Technical Education, New Delhi in 2012. He has previously been the Registrar of Anna University of Technology, Chennai. He received BE in Mechanical Engineering from Tyagarajar College of Engineering, Madurai, MTech in Production Engineering and PhD in Precision Machining in IIT Madras. He was awarded for his PG work, project work in IIT Madras. His main areas of interest are technical education system development, precision machining, rapid prototyping, FEA, biomedical engineering, medical image analysis, and shape memory alloys. He is a life member of ISTE, AMM, and SME of USA. He has been awarded with fellowships of research work done in surface engineering by NSF, USA in 1992 and by NSTB Singapore in 1997 to 1999. He is a visiting faculty in India and abroad in many colleges and universities, including Nanyang Technological University, Singapore, Technical University, Weingarten, Stuttgart, Germany, and taught nanotechnology. He has traveled many countries, including Germany, UK, USA, Netherlands, Singapore, Spain, Switzerland, Malaysia, Brunei, and Australia for his academic works. In addition, he got international travel fellowships from UGC, AICTE, CSIR, and DST. He has successfully completed several projects in India and abroad. He has offered technical consultations in India and abroad to MNCs such as Sony of Japan, Pratt & Whitney of USA, GE of Singapore, iGel of Australia, and also to Railways Coach Factory, Chennai. He was a member of the Technical Expert Committee selected by DST to participate in the Indo-UK Manufacturing Engineering Colloquium held in January 2012. He headed the International Joint Project on Virtual Laboratories on Mechatronics, a real-time web-based project with partners from Julius Maximilian University, Würzburg, Germany, and the University of Madrid, Spain in 2005. He is holding an international patent for the work done in micromachining during his tenure in Singapore. He is a member and director of several Tamil Nadu government advisory boards.
In this episode, we will learn about the modeling of linear programming, where only two variables are allowed, and what is convex and non-convex polygon, and what are the importances of these polygons.
Now, we have to find out the value of x1, x2, x3 using all these 1, 2, 3, 4 and 5. And since there are only two variables, let me go for the graphical technique. Even though this problem can be solved by simplex, let us start with a graphical technique which is a simpler one. Let me say the axis was x1 at the x-axis and the ordinate of say x2 axis. Clear? Now, I am going to use this graph and say this starts from 0. Constraint number 1, x1 plus x2 less than or equal to 45. So, I am writing the x1 and x2, x1, x2 greater than or equal to 0, that is non-negative constraint. Now, let me consider the first constraint, x1 plus x2. What is the minimum value of x1? What is the minimum value of x2? Let us start from the minimum. Now, this is an inequality. That means, it has one inequality like less than 45 and yes or no. Okay. Now, I am going to have the effect of both. x1 plus x2 is 45. What is the minimum value of x1? 0. So, let me consider this equality first. If x1 is 0, what is the value of x2? 45. Okay. And if x2 is 0, what is the value of x1? 45. Good. Now, we got a solution from the minimum condition. Now, we have to graduate this abscissa on the ordinate by, let us put the value of 5, 10, 15, 20, 25, 30, 35, 40, 45. Similarly, here 5, 10, 15, 20, 25, 30, 35, 40, 45, 50 like this. Here also 50, you can go up to 50. Now, if come to this first, if x1 is 0, x2 is 45. If x2 is 0, x1 is 45. If we consider equality, how will you connect them? That means, for any number of values of variable of x1 and x2 starting from the minimum 0, you will be able to draw a line, and the line represents all the points, all the set of values of x1, x2. Am I right? That means, if you draw like this, you take any point over the line, the blue line, that satisfy the equality x1 plus x2 is 45. Yes or no? That is how we have been taught, convinced or mesmerized, something like that. And this is the one. That means, I have drawn a line which satisfies the equation, but at the same time I have to satisfy the inequality. How? If I take any value of x1 x2, that shows the summation as less than 45. How to show that? So, you shade the region below this. And if we take any point here in the triangle, I should not say triangle, it is a polygon, 3-sided polygon. And if we take any point in the triangle, the polygon, that will satisfy the inequality x1 plus x2 less than 45. If we take any point over the line, and that satisfies the equality. So, this polygon looking like a triangle, if I give the name like A, B, C, the polygon ABC satisfy the constraint number 1. That means, we take any point in the polygon, it will satisfy the inequality. Clear? But this is not the only one constraint in the problem. There are 4 more constraints. Yes or no? Yeah. What is the next constraint? The next constraint is x1 less than or equal to 20. Another one? Is it? Yeah. When x1 less than or equal to 20, first consider x1 equal to 20. X1 is 20 here, and x2 does not have any effect on that. So, x2 can, for any value of x2, x1 will remain 20 only. So, how does it be? The line, it should be a line parallel to ordinate, go like that. So, but that is less than also. So, you draw, you shade these regions below. So, the black shaded one shows that x1 is less than or equal to 20. If we take any point on the line, equal, any point here, that will be less than 20. Yes or no? For any value of x2, x2 has no influence on that. Next come here, x2 less than or equal to 40, similar, x2 40. And less than or equal to, so below. So, any point if we take in this rectangle starting from here, go to the next building, beyond the building civil engineering, mechanical engineering, still that will satisfy the constraint x2 less than or equal to 40. Now, this is constraint number 1, constraint number 2, constraint number 3. clear, and each one has its feasible region, and the region, the red one previously is a feasible region for only that constraint, and this one is feasible region for the second constraint, this one third constraint. Any more constraint? You are putting more constraints to me. Lunch hours. Yeah, tell me, what is the next hour, next constraint? Huh? 2? 2x1 plus x2? 66. Good. If x1 is 0, x2? 66. If x2 is 0, 33. So, if x1 is 0, x2 is 66. So, I have to still plot to the 50, 55, 60, 65. So, 66 may be here. So, x1 is 0, x2 equal to 66 here. If x2 is 0, x1 is 33, 35. 32.5 may be here, 33. So, how should I join? Straight line? Yeah, linear. So, join them. So, this is a last constraint, that is a fourth constraint. Now, there are 4 constraints. With that, we have drawn the feasible regions, considering the fifth constraint also, and identified these are the feasible regions. The first triangle only for the first, like that, second, third, fourth. Now, can you find a region, a feasible region, which can satisfy all the constraints? Yeah. Any of you come to the board and name that polygon? Can any of you come? You have selected a nice color, green color, so that you can easily distinguish from all the others. What I was supposed to do, he has done it. Is it right? Has he done a right job? Can you congratulate him? Yeah, very good. So, Prashant has identified this is a feasible region, giving the name as A, already we have given, B has given C. So, this is D, this is E, this is F, this is G, this is H. So, the polygon A, D, E, F, G, H is the polygon showing the feasible region which satisfy all the given 5 constraints. That means, if you take any point in the region or on the sides of the polygon, that will satisfy the inequalities. Clear? A, B, C, D. And this polygon convex. The Danzig says the convex polygon, there are a lot of theorems behind it, but since the linear programming according to syllabus, we need not to go to the theorem and the riders beyond that, we just take the concept out of that. What he says is, in a polygon of n dimension, n sides, it can be 3, it can be 4, 5, 6, here 1, 2, 3, 4, 5, 6, the 6 sided polygon. So, any number of sides can be there, take a point here x and take another point somewhere, anywhere. What do you want to take inside the polygon, here or here or here? Let me take here, I take a point y here and you join them by a straight line, and the straight line should lie in the polygon. That means, all the points, set of points x and x1 values of set of points along the line will be in the feasible region. That is the meaning. Then that polygon is called convex polygon. Only a convex polygon give an optimal solution, even though there are feasible solutions. Then you may ask, sir, what is opposite of convex? A non-convex polygon may be like this. You got set of lines crossing, finally you got a feasible region like this. This was bound by one line, and this by another line, this by another line, this by another line, like that you may get it. But still it is a feasible one. But you take a point here, and if you take a point here, you join them. The line, part of the line is lying outside of the polygon. So, this is a non-convex polygon. The non-convex polygon again may be due to the insufficient data or inconsistent data or by wrong modeling, or sometimes it may be purely theoretical. Clear? So, this is a non-convex polygon. So, for an optimal solution we want to find, we need always a convex polygon. Check whether you get a convex polygon. Now, we have got a 6-sided convex polygon, the points like A, D, E, F, G and H, I remember well. So, this polygon, how many points are there? A, D, E, F, G, H, am I right? There are 6 points. There are 6 points in the polygon, 6 sides and 6 points. And these are the sides of the polygon, and these are the points. And these points are called extreme points. These are called the extreme points. So, in a feasible region or a convex polygon, the region gives a feasible solution. If we take any point here, that will give the feasibility, because they are always less than. When it will become equal? Over the line only. So, the sides of the polygon give the best feasible solution. And in a still better way, you see that the corner points A, D, E, F, G, H give the best feasible solutions. Among them, best feasible solutions or improved feasible solutions, any one of them, any one of the corners will give the optimal solution. Any one of the corner. It may be more than one corner give the optimal solution. If you find out the value of x1, x2 here, 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 here and here, put in the z equation, find out the value of z, then you will get any one of them or more than one of them may give the highest value. The highest value should be same. And clearly known, what is the value of A? 0, 0. That will not, it is feasible, but the lowest value. So, that does not give the optimal solution. Then what is the value of D? What is the value of E? What is the value of F, G and H? You find out and get the coordinate value of x1 and x2, put in the z equation, then whichever gives the largest value or the highest value, that is the optimal solution, or you say the best, the most promising feasible solution. So, the corner points, extreme points gives the best feasible, and any one of them or more than one of them will give the optimal solution. That is a graphical technique what we can find. Since I have not used this proper graph and everything, I am unable to find out. Now, I give it an exercise. You can find out who are the, how this point is obtained. This is known. What is the value of x1? 0. What is the value of x2? 40. Here, what is the value of x1 is 20. Other is 0. That okay. This is known. The remaining, how is this obtained? Intersection of this line and this line. You solve it. This is obtained by intersection of these two lines. This is obtained by the intersection of this slanting and this line. So, by solving it, if you mathematically solve, instead of finding in the graph, if the graph sometimes you miss the decimal 0.3, 0.35 like that. But if you identify what are the corner, by graphical technique, identify how the point of intersection is obtained, then solve mathematically. Find the value of x1 and x2. Then put the value of x1 and x2 in the z equation. Then whichever gives the highest value of z, that is optimal. That is the profit what the manufacturer wants. Can you do it now? Please solve it and tell me. E 5 40. F 21 24. G 20 comma 26. No. You get 26. Are you getting 26? It comes less than that. So you have got a polygon. What is the corresponding equations? 20. Maximally x1 is. That's okay. Is it 26? You sum it up. But that your graph. No, it should be less than that. Maybe 25. Then H 20 0. So which gives the best one? F, any scale or anything. Okay, doesn't matter. You solve with the use of proper graph. So according to this, now we have to conclude the chart. So which gives the F gives the best solution, the optimal solution. For the F value, what is Z? Z 8, 8 21 plus 7 24. How much? Huh? What is the value? 3? 1000, no? This is 1000 bottles, no? 1000. So this is a profit, maybe rupees. That is a maximum profit we get. So now we have found out these values which satisfy all the constraints, but one of them has given the best or the higher value of Z. That is the optimal solution. The product mix is the plant should produce in a production run 21,000 of bottles for medicine A and 24,000 bottles of medicine B in a production run. That is the best one.
At last, these questions will test your understanding. Question number 1, how is the inequality shown in the graph, whereas a straight line represents an equality? The second question, how will you find out optimal solution in graphical technique? The last question is, under what circumstances will you not be able to get a feasible region in a polygon? How will you name the polygon?